In the previous video, we gave an algorithm for computing the derivatives of the area E with respect to all the weights W. This algorithm is known as the back-propagation algorithm, and it is essentially just a dynamic programming algorithm. The key in computing the derivatives is the calculation of the deltas, those deltas, right? And the calculation of the deltas must be carried out from the top layer down towards the bottom layer. Right? So that's why it's called a back-propagation algorithm. It's the opposite in the opposite direction from the forward calculation, which actually goes from the bottom input layer towards the top output layer. So it's called the back-propagation algorithm. In this video, let's look at how we can actually implement this algorithm in Python for our very simple neural network. For a very simple neural network, this particular neural network, right? It's got like 3 layers, and no, actually 2 layers. This is the input layer, right? And then we have like 12 weights for them. We will evaluate the derivatives at the weight values given on this figure. Right, all the derivatives. So the error is actually a function of the 12 derivatives, 12 weights. Right. So the derivative of the error with respect to the weights are still functions of the 12 weights, and those derivative functions are then evaluated at the values of the weights that's given on this particular figure, right? So if you sort of forgot about how derivatives were evaluated, it's not like you compute the value of the function first and then you take the derivative. If you compute the function of the value of the function, then the value of the function is a constant. If you take a derivative with respect to all the weights, then constant with respect to the weights is just a 0, right? You have to take the derivative first, and then you have to take the derivative of the function first, and then bring in the values of those weights to compute the actual values of the derivative. And the 2 input values, x1 and x2, are fixed at 12.5 and 4 respectively, and the 2 ground truth output values, t1 and t2, are fixed at 10 and 1 respectively. So in this Python code, all the weights, all the w's are followed by 3 indexes. You have like 3 numbers behind it, right? Behind every w. Right? The first index is the superscript. It's the layer number, right? So this number is the layer number. So the first 6 w's are all for layer 1. These weights actually. So that's the first index, and then the second index. The second index is actually the first subscript. So if you look at all the w's, it's got 2 subscripts. Right? The first subscript indicates the neuron ID, the neuron index, in the bottom layer, and then not in the lower layer, and then the second subscript indicates the neuron ID in the upper layer, right? And then the W is associated with the connection that goes from the lower layer to the upper layer, right? So the second index is actually the first subscript, and then the third index is the second subscript. Right? Only the weights actually has a third index, right? Because all the y's, all the outputs, and all the logits of each neuron has only has only one subscript. So only the weights have a third index, right? Which is actually the second subscript. And if you want to compare the values, right? So W101 equals to 0.9. So W101, 1 is the superscript, 0 is the first subscript and 1 is the second subscript. It has value 0.9. And then W122 has a value of 0.04. W122, W122, that's this value, has a value of 0.04. So all values are actually corresponding to the values that's displayed on this particular figure. If you compare a value for, say, W221, W221, that has a value of 0.01. So we will still be using the sigmoid function as the nonlinear function inside each neuron. So we need to define a Python function to implement this sigmoid function. Right. And the definition of the function is just a straightforward translation of the mathematical formula of the sigmoid function. So it's a 1 over 1 plus e to the minus z. It's a 1 over 1 plus this amp.exp function is actually the same as this kind of exponential function here, and then minus z, that's the power. And that's our definition for the sigmoid function. So we have a Python implementation of that function. It's just like 2 lines. And then for the backpropagation, we're going to need the derivative of the sigmoid function. So here we have implemented a Python function that's called d sigmoid. It's just the sigmoid with a d in front of it. So in the previous video, we obtained this explicit expression for the derivative of the sigmoid function. So if y is the output of the sigmoid function for the input z, right, then the output of the d sigmoid function should be the derivative of the sigmoid function should be 1 subtract y multiplying y. Right, so in the d sigmoid function, so in this particular function, we first call the sigmoid function to obtain the output y for the input z, and then we just return 1 subtract y times y. Again, it's just a straightforward translation of this mathematical formula. And then we have implemented the backpropagation algorithm inside of this Python function named backprop. It's going to take 4 input values. So x1 and x2 are the inputs of the to the neural network, x1 and x2. And then t1 and t2 are the ground truth, t1 and t2 here. So that's going to be the inputs to this backprop function. And this backprop function is going to return the output of this particular function, of this backprop function, is going to be the it's actually a Python tuple with the 12 derivatives of the error with respect to the 12 weights. And then inside the backprop function, the calculations are separated into 2 stages. We have 2 stages of calculation. That's the first stage, and then that's the second stage. In the first stage, we only carry out the forward calculation. So the first stage is called forward. We have a comment here. That's a forward calculation. In this forward calculation, we go from the bottom input layer towards the top output layer. And during this process, during all this forward calculation, we compute and store all the logits and the neuron output, all the z's and all the y's that's inside of every neuron. So during the forward calculation, all the logits, all the z's, z11, z12, z21, z22, and the corresponding y's, y11, y12, y21, y22, are computed and then stored in variables, inside of variables. Right. So if we look at the codes, z11 equals to the weighted summation z11 That's the Z11, right? It's a logit. It's the logit. It's just equals to the weighted summation of x0, x1, and x2, with all the weights, given by W101, W101, W111, W111, and W121. And then the neuron output Y11 just equals to is obtained by, so Y11 is obtained by just calling the sigmoid function with Z11 as its input. And we also computed and stored the values for Z12. And the Y12 is computed in a similar way, except that the weights for computing the logits must be changed to the weights corresponding to the three blue arrows that's pointing into this particular neuron, right? So it's W102, W112, and W122, W102, W112, and W122. And then the calculation is kind of similar to this particular neuron. And that's all the calculations for the first layer, right? So once we got the Z11, Y11, Z12, Y12, we have finished the calculations for the first layer. We then go on to the second layer. That's layer 2. Right, that's layer 2. We also compute and store the values for Z21 and Z22, Y21 and Y22. Right? So the calculations are pretty similar, except that all the weights must be replaced with the weights for the second layer, and then the input values are actually the output values from the first layer. Right? But the equations are actually identical. It's almost the same, except the indexes for the weights have been changed to the second layer's weights. After we have finished the forward calculation, the logit Z, the neuron output Y for every neuron, are then obtained, and then we have stored them inside the corresponding variables. And we are now ready for the second stage, which is actually the backward calculation. Right. And in the back-propagation stage, we start from the top layer, and we have to first compute the deltas for the top layer. Right. So let's look at our back-propagation algorithm. So we must start with the deltas for the top layer. Here, capital L equals to 2 for our simple neural network, right? Capital L equals to 2. And we have actually 2 deltas to compute because the subscript J has only 2 values, 1 and 2, right? We only have T1 and T2, so J goes from like 1 to 2. It has only 2 values. So delta, to compute the 2 deltas at layer 2, we can just use this formula, these two equations directly, right? So we need to use the ground truth T1 and T2, and also the derivatives of the sigmoid function that's evaluated at the logits Z21 and Z22. So that's the input to the D sigmoid function, Z21 and Z22. And then the stuff that's multiplied with the sigmoid, the derivative of the sigmoid function is the T subtract the Y, the corresponding Y. So it's T1 subtract Y21, because capital L equals to 2. And then T2 subtract Y22 with the minus sign. So that gives us the 2 deltas at the top layer. And after we have obtained the 2 deltas for the top layer, we can compute the derivatives of the error with respect to the 6 weights at the top layer by using this particular equation. Right, so partial E, partial W. Here L is 2. Right? So L is 2. L is 2. So 2 subtract 1 is 1. So the Y values we're going to use are from the first layer. It's going to be Y1I. Right? with the index of I being identical to this I here, and then the subscript j be identical to this particular index here. So let's look at these six equations. These six equations just computes the corresponding delta multiplied with the corresponding y. Right? So if we look at just the first equation, it's a dE over dW 201. Right? So L equals to 2, right? So for all the six equations, for all the six expressions, dW, the first subscript, the first index is always 2. Right? It's all 2's. Right? Because L equals to 2. Right? And then for dE over dW 201, I equals to 0, and j equals to 1. So j equals to 1, that's delta 2 1. I equals to 0, right? So it's y 1 0. Y 1 0. Right? That's exactly the translation of this particular expression. So as long as we actually get the indexes right, the calculation is going to be correct. And then we move on to the calculation in layer 1. The calculations for the deltas in layer 1 must use the deltas in layer 2. So we have to use this particular equation to compute the deltas in layer 1 now. And this expression actually has to use, so if L equals to 1, 1 plus 1 is 2. So we must use the deltas in layer 2 now. And we have actually computed the deltas in layer 2 and stored them in these two variables, right? And the summation over index k, the summation index k actually has only two values, 1 and 2, because for layer 2 we only have like two different deltas, right? Delta 1 and delta 2. So this summation over k actually goes from 1 to 2. So when j actually equals to 1, so j equals to 1, right? Delta 1 1 here is going to equals to what? Delta L 1 plus 1 is 2, right? So delta 2 when k equals to 1, it's delta 2 1 times W 2 when j equals to 1, right? So W 2 1 k equals to 1. K equals to 1. So it's W 2 1 1. And then plus when k equals to 2. When k equals to 2 is delta 2 2 multiply W 2 1 2. W 2 1 2. And then multiply with the derivative of the sigmoid function evaluated at when j equals to 1, it's z. L equals to 1, right? 1 1 z 1 1. Right, that's delta 1 1. Again, it's just a straightforward translation of this particular mathematical equation. Okay. So the calculation for delta 1 2 is similar. And once the deltas for layer 1 are obtained, we can compute the derivatives of the error with respect to the 6 weights in layer 1. And the only thing that we have to sort of pay attention to in this particular layer is that now the superscript for the y, L equals to 1, right? So it's 1 subtract 1, it's 0. So it's y 0i. Right? So we have to use this part of the algorithm. So y 0i actually equals to xi. Right? So we must use the corresponding input x value with the same subscript. Right? So that's why we have x0, x1, and x2 here. Right? Because all the y 0i are being replaced with xi. Just in the previous video, we also obtained analytic expressions for 3 derivatives. We obtained analytic expressions for 3 derivatives, which is dE over dW 211. Its expression is here. And then dE over dW 212. Its expression is right here. And then dE over dW 111. and its expression is this very long thing, very long expression. Right. So we have analytic derivations for at least 3 derivatives. Right, we have obtained 3 analytic expressions for 3 derivatives. So we can also compute these 3 derivatives using the analytic expressions we have obtained, right? And we can use these 3 derivatives to actually check the correctness of our backpropagation algorithm. So here, DE-DW211 underscore check is just a straightforward translation of the analytic expression into Python code. It's T1 subtract Y21 multiply 1 subtract Y21 multiply Y21 multiply Y11. Right. And for DE-DW212 underscore check, it's exactly implementation of this particular formula. And again for DE over DW11 check, DE over DW11 check, it's exactly implementation of this particular analytic expression. So we can compare the 3 derivatives that's computed using those 3 analytic expressions with the corresponding derivatives computed using the backpropagation algorithm. So we're just printing out the difference. We're just subtracting them, subtracting the derivatives computed in the 2 different ways. And if the differences are within machine precision, then it is sort of very likely that our backpropagation algorithm is actually implemented correctly. And at the end of the function, we just assemble all the derivatives into a Python tuple, and then just return it. Just return this tuple. And after the definition has finished, and at this particular line, we actually call this particular function backprop. So definition of the backprop function goes from the line 35 to line 93, and then here on line 96 we call the backprop function with the correct input. So x1 and x2, 12.5 and 4, and then ground truth is 10 and 1, 10 and 1, and then the output of the backprop is being assigned to DE-DW, and we can run this entire program. We can run this entire program by just clicking this thing. And then we sort of see this particular output, this spring output. Right? And this is 2.2 something multiplied 10 to the minus 16. This is exactly 0, and this is 5.55 something times 10 to the minus 17. So 10 to the minus 16, 10 to the minus 17, those are all within machine precision, which means that the difference between the analytic calculation and the backpropagation calculation are identical to each other within machine precision. So it seems that our implementation of the backpropagation algorithm for our very simple 2-layer neural network based on this particular algorithm that we have talked about last time. This dynamic programming algorithm is indeed correct.